Okay, so let us come back to where we left. So, we were using Kroger-Wink notation and we started writing different defects as a reaction using this Kroger-Wink notation. So, this one was that we discussed last lecture, Schottky relation, Schottky defects. So, as you can see it is a reaction, it can be written as a reaction. Next is Frankel defect. So, now we will try to write Frankel defect as a reaction. So, you remember in Frankel defect what we have is a cation moves on into a interstitial. So, we can write something M, which is the metal, which will be the cation, it will move into a vacancy, sorry, interstitial. So, it will create a vacancy and this vacancy will not have any charge where it should have charge, and assuming that the original charge of the metal was 2 units. So, it will become 2 negative charges and the interstitial metal will be in the interstitial, and therefore, in the interstitial there should not have been any charge, and therefore, it will be represented at 2 additional positive charges. And to trace the interstitial sites, you can add here vacancy interstitial. It will not make any difference to the overall reaction and when we look into the thermodynamics, but this will only help us understand number of interstitials that are being used or created and so on. So, this is the Frankel relation or the Frankel defect which can be represented as a reaction. Now, we will also look at, so far we have looked only at atomic defects. Now, let us look at if electrons and holes are generated. So, the advantage of this defect reaction is that even electron and holes can be represented by these relations, by these reactions, and hence the thermodynamic equilibrium concentration can be obtained. So, next let us look at intrinsic ionization of electrons. So, from nowhere or basically from a perfect crystal, you can have one electron and one hole created. But remember, in a defect reaction we also wanted to maintain mass. So, you can represent it something like this. So, electron with no charge effectively is moving on to create one electron which has a negative charge and a hole which has a positive charge. Now, these electrons and holes here you will realize are non-localized, and basically it means that this electron is not present at any particular site, they are in the conduction band. So, this is non-localized, not any particular site cannot be said to be possessing these electrons. So, in that sense it is non-localized in the conduction band. Now, on the other hand, if we assume if these charges or electronic defects are localized, which would mean that this electron has to be at a particular site, and therefore, it can be represented by something, let us say metal, and let us put iron over here. So, since this iron has to, this electron as well as a hole has to go somewhere. So, we can say that one of the iron atoms is taking the negative charge and one of the iron atoms is taking the positive charge. Effective, remember it is effective negative or effective positive charge. What does that mean? That from whatever it was supposed to have, it is one less, and over here it is one more, which means that if we are talking about Fe, this Fe 3 plus ion is getting converted to Fe 2 plus and Fe 4 plus. So, you see that in the matrix Fe was in 3 plus valence state, but because of presence of extra electron and extra hole, basically creation of a electron and a hole, and which are getting localized onto these metal atoms, this charge from 3 plus has been reduced to 2 plus. So, it is 1 less than 3 plus. So, it is 1 represented as 1 negative, and this is 1 more than, this is 4 plus, which is 1 more than 3 plus. So, it is represented as 1 dot. So, this is the intrinsic ionization of electrons when this is not localized, and when it is localized as on any particular atom. So, it could be anything, something, it could also be something like, let us say, metal 2 plus going to metal 1 plus 3 plus. So, even this will be represented by something like this. So, here they have basically one electron accepting one electron, here it is accepting one hole. So, all these are examples of electronic defects which are localized. Now, let us look at how to write the defect reaction for a non-stoichiometric system. Even if it is a non-stoichiometric system, remember that the number of sites present in the system would still maintain the stoichiometry. Okay, so, a non-stoichiometry can be occurring because, let us say, in a system like MO, a part of the oxygen escapes and forms goes into the atmosphere as oxygen gas. So, it will become so let us say it was MO2, so MO2 minus X. So, some part of the oxygen elements have left the system and into the atmosphere. How do we represent? So, basically oxygen at its oxygen site, which can be which has neutral charge, it forms vacancy at oxygen site, and let us assume that it leaves in a neutral state, meaning that it remains with the charges remain with the site where it was there, because that we have to maintain charge neutrality. Therefore, the vacancy site will have 0 charge, effective 0 charge, but in absolute terms there is a -2 charge over here. So, in absolute terms it has -2 charge. And where does the oxygen atom actually go? It escapes as gas. So, 1/2 O2 gas. This right now the charge over here is localized onto vacancy. Now, this vacancy can delocalize the charge, meaning it can let go the charge, and therefore, it can happen something like this. It may further go on and it will have no absolute charge, meaning in effective terms it is positively charged, the electrons have left it. In a relative term it is 2 positive, and where do the electrons go? It has got delocalized. So, this is 2 electron with negative charges and it has gone into the conduction band of the system. So, overall this reaction can be written as vacancy at oxygen site with 2 positive effective charge with 2 electrons which are delocalized plus 1/2 O2 gas. So, the 2 electron is delocalized. Now, if let us say again like the previous case, this electron is not delocalized, but it gets, if electron or charges get localized on a metal site, because mostly metal will have variable valency. So, this can be represented. So, this 2 electron will have to move on to some metal site. So, it will be represented by something like this. Let us say that there are 2 electrons and they are moving to 2 different sites. So, each of the metal sites get reduced by 1 charge. Therefore, to begin with they are neutral, oxygen site is neutral and it forms vacancy which has effective positive charge, 2 positive charge plus 2 negative charge plus 1/2 O2 gas. So, you see that we are now able to represent this kind of defect as a reaction. Let us talk about still another defect, which is presence of dopants. So, mostly in semiconductors you would know that dopants are added because they create charge with defects which lead to increase in electrons or increase in holes. So, presence of dopants as impurities. Let us look at that. So, what do we know? That whenever dopants are added, it may significantly affect the concentration of it can significantly affect the concentration of defects, may significantly affect the concentration of defects. Now, these dopants that are being added, they can have a valency similar to silicon or it can have a valency different from silicon. So, first let us distribute it into these two categories. When it has similar valency as silicon, which has a valency of 4, then it is called homovalent, meaning same valency as host. In case of silicon, it means plus 4, it means 4. And if it is different in valency than the host, which in a particular case silicon, if it is different from 4 like plus it is 3 or 5, then it is called aliovalent. Now, this aliovalent are the ones which are of interest to people in semiconductors. Why? Because they can either donate electrons or they can accept electrons, and therefore, they can change the concentration, relative concentration of N and P, the number of electrons and number of holes. So, let us look at example boron. Boron, if it is present at a silicon site, silicon which should have 4 valence, but boron has 3. So, it is trivalent. And when boron is there, it means that it has effectively one negative charge, and therefore, it will emit one hole, because it has effectively one charge, and if you look at the charge neutrality for this reaction, then you would realize that there should be a hole generated. So, you can see that this equation can so easily predict that a hole has to be generated whenever for each and every boron atom that sits at the silicon site. Now, let us look at the other type of example as dopant, which is phosphorus, which is pentavalent. So, if phosphorus is sitting at silicon site, it has effectively one extra positive charge. Compared to boron, which had extra negative charge, it has one extra positive charge, which means that there should be a electron generated for this. Now, this can also be represented by other broken bond models, that it has one extra electron which is not satisfied. So, this extra electron will move on to the conduction band. But in terms of reaction also, you can show the same thing, that phosphorus sitting at silicon can be represented as one with effective positive charge, and therefore, to maintain charge neutrality, there will be an electron generated over here. So, again you see that this defect reaction can be a very useful method to understand what is going on, what will be generated even in terms of holes and electrons, not only in terms of defect lattice type of defects. Now that we have looked at the defect reactions, let us look at the usefulness of it in predicting the equilibrium concentration. So, what is the basic thermodynamics when we are using a defect reaction? what it says, what we know is that for a reaction which goes like this, A moles of A component, B moles of B component, if they react and form under equilibrium, they form some C moles of C component and D moles of D component. Then what we know is that the delta G, the free energy change for this reaction, can be given as this. The delta G naught is at the standard state plus RT ln A. So, what we have here is AC, which means activity coefficient of the C component, and to the power small c, which is the number of moles. So, you have to be careful on which C we are writing here. So, let me try to be a little bit more clear. So, this is the capital C, meaning C element C component, activity coefficient of C component to the power C, which is this small c. Similarly, activity coefficient of D component to the power small d, that is how many number of moles of this D is. Activity coefficient of A component to the power A, activity coefficient of B component to the power small b, which is how many number of moles of B are there. So, what is A? A is activity. For respective component. Now, at equilibrium, we will have delta G equal to 0, meaning the reaction has come to an equilibrium, the reaction is not moving. We have equilibrium number of A element, A component, B component, equilibrium component of C and D. So, at that condition delta G is equal to 0, and therefore, what we have is a relation like this. If we represent this by K, meaning K is equal to this quantity. Now, this quantity can be approximately said to be equal to the relative fractions. So, if the equilibrium fraction of C component is x c to the power small c. So, again let me, so here also it is not very clear, I will just so we have equilibrium concentration of C to the power C, equilibrium concentration of component D to the power D, that is how many moles there are, equilibrium concentration of A to the power small a, which is the number of moles. So, now we have a relation similar to that we had derived earlier. Actually, there is one more step before that. So, what is that step? We know that delta G naught is equal to okay, here is ln missing. Or in other words, we have K equal to exp, which is the exponent, because this is log. So, we are now taking the exponent of everything and dividing it by RT. So, what we are doing here is taking exponent on both sides, and hence we get rid of the log term and we get equation for K. So, first thing that you should note is that here this equation, here we are using R, meaning whatever energy terms we are using, delta S or delta H, it has to be in per mole term. If we again translate it to per electron term, then you can use Kb. Now, here delta S naught is nothing but what we had earlier called as the delta S formation. So, that is equal to delta S vibration, that is the same, and similarly delta minus delta H naught here is nothing but delta H or minus, since we are talking about minus delta H formation. So, whatever it is about one vacancy or it is one Frankel pair or one Schottky pair, it can also relate to those formation energies also. In this particular case, it is talking about the change in enthalpy when this reaction goes from here to here. Now, this is the equation that is very similar to what we had obtained earlier. So, here now we can write it like this. So, now whenever you write a defect as a reaction, you would know all these quantities A, B, C, D, the uppercase A, B, C, D and the smaller case A, B, C, D, and therefore, you would also know these quantities, and relative to that the thermodynamic quantities delta SF and delta H also would be known, and therefore, from this you if you know the right hand side, you can get the left hand side, and in left hand side if there is one or two particular components that you do not know, then you can find that one or two component and or at least the relative ratio between the two. So, that is the usefulness of writing defect as a reaction. So, instead of going through all the entropy or the configurational entropy and all those terms, we can see that we can directly reach over here. So, another thing to understand is that when we write this equation, because we have already seen derived the similar equation using configurational entropy. So, we know that this is not the configurational entropy, this is the vibrational entropy. So, we have to be aware of that when we write this equation like this is not the configurational entropy, all that has been taken into account over here when we get this relation. So, instead of going through all that process of configurational entropy, we can just directly use this defect reaction and get the equilibrium concentration. Okay, so, now let us apply this knowledge to some of these reactions that we just talked about. So, let us say we go to, let us revisit Schottky defect. Now, how did we write the Schottky defect reaction? So, we wrote it something like this. So, Schottky defect is what is Schottky defect? It is the vacancy at cation and vacancy at anion in that particular ratio, and here we are assuming it is MO. So, M plus 2 O minus 2, and therefore, vacancy at O site will be equivalent to 2 positive charges and vacancy at metal site would be equal to 2 negative charges, and therefore, this rate constant Ks would be equal to x VO dot x Vm prime double prime x O at O into x M at M, and this we know is equal to the thermodynamic quantity, which is delta SF by R times Exp minus delta HF Schottky defect. Now, over here what else do we know over here? What we know here is that what is the fraction of O on O. First, what is the fraction of this fraction M on M. Similarly, what we also want to know is the fraction XVO XVM. Okay. So, there are certain assumptions we will have to make here. One is that this particular defect is the dominating defect. Let us say if the vacancy were being produced by some other mechanism also, then we will not be able to say that this relation is the final one, or the vacancy concentration would also be influenced by the other reaction. So, we have to assume that this is the dominating defect. So, one thing that we have to assume is that Schottky defect is dominating this is one assumption. Second assumption is that defect concentration is very small. Why do we want to say that? Why we want to say that is because in that particular case we will be able to say that fraction of oxygen site on oxygen is approximately equal to 1. If there were too many vacancies, let us say 20% defects, meaning oxygen has there are 20% vacancies of oxygen, then O and O will not be equal to 1, and then it will we will have to evaluate, it will be a lot more complicated and difficult to evaluate the fractions of VO and VMM. So, the one of the assumptions is that defect concentration is small. This is also to ensure that activity coefficient which has been related to X, which is the molar fraction of the defects. So, this equation, this equality is also true when defect concentration is small. Similarly, the fraction X mm is also approximately equal to 1. So, we have these two assumptions. Because of this we get this relation, and another assumption in these particular cases, or it is not really assumption, but it is a derivation from this, is that when you have all these conditions true, what it also means is that XVO, actually it should be the number of vacancies, it is also equal to XVM. This is getting derived from the fact that number of vacancies is equal to number of the number of vacancy at oxygen site is equal to the number of vacancy at the metal sites. So, this equation can also be represented as fraction of XVO equal to fraction of VMM. Now, when we have this, we can say that XVO dot dot into XVM is equal to EXP Now, since this is equal, so we can take a square root, and therefore, XVO dot dot XVM is equal to square root means 1 over 2 factor over here. So, this is a relation that we had derived earlier, and you see that we have been able to derive it here too. So, this is one example. We will continue with more examples in the next class. Thank you.